audible enough? Let me know if I am audible enough. Okay. Am I still audible? So I have to use the mic for me to be clear. So just confirm if I'm audible now. And let me know if everything is clear on your end. Otherwise, good evening. Let me start from the top. Good evening, Miss Sandra, Miss Limpo, Miss Mary, Mr. Ran, damn formal, Miss Esther, Mr. Harold, Miss Seychelles. Hey, news in a bunch. Seychelles, 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 Hatembo, Hatembo. Good evening, Miss Mary Easton. Is it a female? I think it's a male. Good evening, Miss Mary Rose. Good evening, Miss Memory, Miss Naomi, Miss Margaret, Miss Betsheba, Miss Matilda, Miss Karen. Okay, I think I've mentioned everyone. Miss Josephine, Miss Dorothy, Miss Anna, Miss Lilato. Okay, okay, Mr. Easton. All right, so I hope I'm audible. If I am audible, then that means we can start with our live class. So this week in the online biology class, we're looking at diffusion, osmosis, as well as active transport. Today in the morning, a tutorial video was sent based on diffusion. I hope you've watched it. And this is just a class to emphasize on what was taught in that tutorial video. Otherwise, I hope we are all doing fine. I hope we had a good day. Otherwise, it's just hot. Ish. It is hot. Kwapia, guys. It's too hot for one to function properly. But otherwise, well, I hope we are drinking water. These are the times where you have to take a lot of water. So drink water even if you're not feeling thirsty. Kuma mans, it's very much important. So we're looking at diffusion, and that should be done before 21 hours because I believe there's a live class as well for science. So I should be done before 21 hours. So yeah, I can start, right? Tingayambe, Tingayambe. All right, so everyone is saying that I can start. So the objectives for this live class, we're going to look at the definition of diffusion. We'll define what diffusion is. Then we're going to look at the factors that affect the rate of diffusion. Then lastly, we're going to look at the importance of diffusion. Okay, so these are the objectives for tonight's live class. Once we are done with this live class, you should be able to know what diffusion is. You should know the factors that affect the rate of diffusion, and you should also know the importance of diffusion. So quickly, let us define diffusion. So definition: this is the movement of particles from their region of higher concentration to their region of lower concentration. Simple definition: diffusion is simply the movement of particles from their region of higher concentration to their region of lower concentration. So here we're seeing that particles are moving from where they are highly concentrated and they are going to where they are less concentrated. We've got two diagrams there. We've got one where I'm sure you can see those blue dots. Okay, so if you look at the first square, you will notice that on the left side, we've got a high concentration of the blue dots than on the left side. I mean, on the left side. Okay, if you focus on the square, the first square on the left side, okay, you will notice that is this a square or a rectangle? Anyway, that box on the left, you will notice that there's a purple line, right, which is demarcating the two sides. And the side which is on the left, there are more blue dots than on the right. So meaning the side on the left is highly concentrated with the blue dots, which are particles in this case. So those blue particles are highly concentrated on the left side. And after some time, we are seeing that now the right side is also equally concentrated with the blue dots. What has happened? Diffusion has taken place. We are seeing that particles have moved from their region of high concentration, which is on the left side, to their region of lower concentration, which is on the right side. So particles have diffused. That is a diagrammatic representation of diffusion. So again, we've got another diagram there where we've got red dots. Okay, so you can see that there's a region of high concentration, then particles are going to move to a region of low concentration. So basically, diffusion is simply the movement of particles from their region of higher concentration to their region of lower concentration. So for example, if someone is cooking in the kitchen, you are able to tell, say, we're frying a kankuku. Okay, we're frying a kankuku. And how are you able to tell? Because particles are moving from that kitchen to where you are. Okay, so where you are, there's less concentration of the particles. Kitchen, it is highly concentrated with the particles that are coming from the source of cooking. Okay, so yeah, diffusion is simply the movement of particles from their region of higher concentration to their region of lower concentration. Muntu ngata spray aka perfume pa akamboenda, particles are going to be diffusing from the body to the rest of the environment. So the body is highly concentrated with the particles of the perfume. The rest of the environment is less concentrated. Therefore, the particles will start moving, they'll start diffusing from the body going to the rest of the environment. So that's basically the definition of diffusion. This is the movement of particles from their region of higher concentration to their region of lower concentration. Now, what you need to understand is that these particles that are diffusing or that are moving from where they are highly concentrated to where they are less concentrated, they are moving at a certain speed. Okay, they are moving at a certain speed or rate, and this speed can be affected by different factors. There are different things that can lead to a change in the speed or in the motion of these particles. So note that particles, as they are moving at a certain speed, they are moving at a certain rate, which can change depending on different factors. This leads us to the factors that affect the rate of diffusion. So, factors that affect the rate of diffusion. The first one is concentration gradient. Concentration gradient. Now, concentration gradient, the definition is this is the difference in concentration of particles between two regions. That is the definition of concentration gradient. It is simply the difference in concentration between two regions. So as you can see here, there's a line, right, which is a membrane. And on two sides, we've got blue dots, which are particles. You can clearly see that on the left side, we've got more blue dots than on the right side. That simply means there's a difference in concentration between these two sides. And that difference in concentration is what is referred to as concentration gradient. The difference in concentration between two regions. Mukakaona kaka diagram aka. Ku left kuli tuma dots twa blue na ku right kuli tuma dots twa blue, but ku left ntwa mbiri kuchira ku right. There's a difference. So that difference is what we refer to as concentration gradient. So concentration gradient is simply the difference in concentration between two regions. Okay. Now, the higher the concentration gradient, the faster the rate of diffusion. In other words, the more the difference, the faster the particles will move to where they are less concentrated. So if the difference is too much, we will notice that particles will move faster. An example is smoke. It moves fast because you find that the difference is wide, it's too much. So smoke will start diffusing to the rest of the environment, trying to fill up the rest of the environment, which is less concentrated with a smoke. Okay, so make sure that you capture the definition of concentration gradient. It is simply the difference in concentration between concentration of particles between two regions. And again, if you look at our diagram here, on the left side, we've got more blue dots than on the right side. That simply means on the left side, we've got more, and on the left we've got more, on the right we've got less. That simply means there's a difference. Okay, difference in what? In concentration. That is concentration gradient. Are we following, my excellent biology students? Are we following? Are we understanding, Mr. Easton? Are we following? Are we understanding? So as you are watching, you can as well like the video. You can as well like the video. And if you haven't yet subscribed, make sure that you do so. I'm kindly asking that you subscribe. Otherwise, I was going through the paper for biology 2024, and honestly, that paper was easy. The paper was quite easy. So obviously next year it will be a bit, but we are going to make it. Truth of the matter is we're going to make it. So that's concentration gradient. I hope we have no questions on concentration gradient. So we can move on to another factor that affect the rate of diffusion. So if we're talking about factors that affect the rate of diffusion, we're simply referring to factors that affect the speed, the motion of that particle which is diffusing. Okay. Another factor is surface area of diffusion surface. Surface area of diffusion surface. So I wish I could draw on this thing, but let me see. Let me try and do this. I think I can, so that I can clearly explain this point here. So just a minute. Just give me a minute or two. So surface area of diffusion surface. So what they are saying here is that the larger the surface area of the diffusion surface, the faster the rate of diffusion. So the larger the surface area, the larger the space, the larger the surface area of diffusion, the faster the rate of diffusion. I need to use a diagram to explain this. So just give me a minute. Oh, by the way, when it comes to YouTube, you can find that some students are behind, okay, in terms of like for some students, you find that they're still on the definition of diffusion. Okay, so if You are behind. You can tap on your screen, you'll see there's like a red line. Just drag it until the far end, you'll be up to date with the live class. Okay, so this is what I want to now do. Mhm. Okay, just trying to my bundles were done. I had to buy. Sorry about that. So let me just put up the screen and we shall continue. Otherwise, please let me know if I'm audible. Let me know if I'm audible. Hope I'm still audible. Let me know if I'm audible. Wonderful. Thank you, Mr. Easton. So unfortunately, I can't draw. So I'll try by all means to explain the best way possible. So imagine we've got two surface areas. Yeah, we've got two surface areas. This one which I've put up, and then we have another one. Let me put up another surface area. We've got this other one. Okay, so we're going to say this one, the small one, it is surface A. Then the big one is surface B. Which one amongst the two surfaces are large? Let me ask that question. Which one amongst the two surfaces are large? You will agree with me that this one, okay, which I've said surface B, it is large, isn't it? So this is a diffusion surface, meaning particles will penetrate through this surface going to the other side. Okay, particles will penetrate through this surface and then they'll go to the other side. So particles are diffusing. Now, between the two surfaces, this one which is large and this one which is small, you notice that more particles were able to diffuse through this surface than this one, because because it's large, so it will accommodate more particles as they are passing through it, as they are penetrating through it. So this point is simply saying that the larger the surface area of diffusion surface, the faster the rate of diffusion, meaning the more the surface area, the more the surface area, the larger the surface area, the more the surface can accommodate particles that can pass through it. I hope you are clear on that point. So the larger the surface area, the faster the rate of diffusion. Okay, are we clear with the explanation? Are we clear? Okay, so the larger the surface area, the faster the rate of diffusion. So the surface area of what? The surface area of the diffusion surface, meaning a surface through which particles can penetrate going to the other side. Are we clear? Mr. Easton, are you clear? Or I should explain again? Are you clear, Mr. Easton? Okay, Mr. Easton is not clear. Let me explain again. So um, imagine this is a net. Yoterako tennis. I'm sure you are familiar with that. I don't know what they call it. I think it's a racket, if I'm not mistaken. Okay. Imagine it's a racket. And obviously, on that racket, there's something like a net on it, right? Where that tennis will bounce off and then, yeah, as they are playing, isn't it? So imagine these are two rackets. We've got this one and we've got this other one. Okay. I hope you're following. We've got the small one, and then we've got the big one. If you were to be asked which one can accommodate more what's this dust that can pass through it going to the other end, to the other side of the racket. If you're going to throw dust from the front and then it's going on the other side of the racket, which one amongst the two will accommodate more dust? Obviously, it's this big one, isn't it? Because it has got more space. In other words, it has got a large area which can accommodate dust passing through it going on the other side of the racket. So it's like things, let me try to put it this way because I have to make sure that you all understand. Let me try to do this. So uh, this is the side view of the big surface, of the large surface area. Okay, and then this is the side view of the smaller one. Side view of the smaller one. Okay, so we've got this side here. Let me try to do this. So if things are going to imagine this round thing, the surface area. Now we're looking at it on the side view, like kumbali musima sides. If you're looking at it from the sides, okay. So if things are moving from this side, going to the other side, let me do this again. If things are moving from this side going to the other side, same applies to here. If things are moving awe ni nchito yamene nchita hapa. So let me do this again. If things are moving from this side, okay, going to the other side, okay, hope you can see that. You will agree with me that this small thing cannot accommodate as much particles as this large surface area. This small surface area cannot accommodate as much particles as this large surface area. Let me bring it home. Imagine there's a room, there's a house. Then this house has got tumibo, it has got holes. There's one big hole which looks like this, and there's another small hole which looks like this one. If that room, there's smoke inside, which hole will allow more smoke going outside? If there's a house, there are two holes. There's a large hole and like a small hole. And then inside the house, there's smoke. Among the two holes, which one will allow more smoke going outside? You're going to tell me that it is the large one, isn't it? Because it is large. Therefore, it will allow as much, it will allow more smoke going outside, isn't it? Now, when we're talking about a diffusion surface, we're simply talking about a surface that is permeable. A surface that is permeable simply means a surface that something, particles can penetrate through, can pass through. Munga mweye mangenera mfwiti muchipupa yangena mfwiti tipa. That mfwiti has penetrated through the wall, isn't it? Meaning the wall is permeable for that mfwiti. Lack of a better example. Okay, so when we're talking about the diffusion surface, it's just a surface through which particles can penetrate, they can pass through. So there are two surfaces here, this one and this one. And both of them, they are permeable, meaning both surfaces can allow particles to pass through them. So which amongst the two surfaces will allow more particles to penetrate through them? It is obviously this large one, isn't it? Because it has got a larger surface area than the small one. Are you following? So it has got a larger surface area than the smaller one. Both of them, they are diffusion surface, and I've said that diffusion surfaces, they are simply surfaces through which particles can penetrate through, they can pass through. Okay, and when you look at the two surfaces that we have here, one is large, the other one is small. So the one which is large, it will allow more particles. It will allow more particles to penetrate through it. Therefore, it can accommodate more particles than the smaller surface. Since that's the case, you will notice that particles will be able to diffuse faster going on the other end, on the other side, when they penetrate through a large surface area than the small one. Are we clear, Mr. Easton? I'll give an example of lungs. When you breathe in, oxygen goes into the lungs. Inside the lungs, we've got an air sac. Now, these air sacs, they are numerous. Why? To simply increase the surface area for faster diffusion. They are numerous to increase the surface area. So the surface area has to be large in order for diffusion to take place at a faster rate. That is why we're saying that the larger the surface area of the diffusion surface, the faster the rate of diffusion. Diffusion surface, do not let it confuse you. Diffusion surface simply refers to a surface that can allow particles to penetrate through it. Okay, are we clear, my students? No one should be left behind. Are we clear? Okay, thank you very much, Mr. Easton. I'm glad you've understood with the examples I've given. Okay, So I'm happy that we are clear. So please, and this one can also confuse us. Going back to this one is saying surface area of diffusion surface, right? But this one is saying thickness of diffusion surface. Thickness of diffusion surface. So when we're talking about the thickness, remember upper, I said that diffusion surface, it is simply a surface that can allow particles to penetrate through it. Particles are penetrating through it, meaning it is permeable. Particles can penetrate through it. That's the diffusion surface. Diffusion surface is a surface that can allow particles to penetrate through it. Now, when we are talking about the thickness of the diffusion surface, here's what we mean. Here is what we mean. So we've got this one. I'll put it like this: thickness, and then let me put another one. We've got another one which is like this. So you can see that this one is thick compared to this one. And by the way, this is the side view of the diffusion surface, meaning particles are moving from this side. They are moving from this side, uku area uku. So imagine, I want you to imagine, we're going to use our imagination. Imagine we've got particles, a particle, we've got another one here, we've got another one here, we've got another one there. These particles are this side. Now these particles are going to penetrate through this surface, okay, this diffusion surface. They'll penetrate through it and they will come to this side. So in fact, let me just put an arrow so we can understand. So this is an arrow. So these particles which are this side, the particles which are this side, they'll penetrate through this thickness, this surface, then they'll come this side. Okay. Hope we can see the arrow. Hope we can see the arrow. Like that. Same applies to here. We've got particles, okay, on one side, and these particles, they have to diffuse, meaning they have to go on the other side. They have to diffuse, my students. They have to move, going to the other side. Okay, let me add another one. Okay, just one more. Okay, so these particles, they have to diffuse, going on the other side. So let me put an arrow which is going to be more visible. So they have to diffuse going on the other side. So if you look at the two surfaces, this one is thick, this one is thin. So when we're talking about the thickness of diffusion surface, we're simply looking at the distance that it will take this particle to move from this side to this other side. Mwaona distance iri hapa, distance iri hapa. So you will agree with me that it will take a bit of time for this particle to move from this side going to the other side. It will take a little bit of time. But when you look at the other diffusion surface, which is thin, it won't take as much time. It will take just a short while. It will be faster on this surface than on this surface. So you notice that particles will diffuse faster when the diffusion surface is thinner. That is why they're saying that the thinner the diffusion surface, the faster the diffusion rate, meaning the faster the rate of diffusion, the faster at which particles will move going to the other side. So here, particles will take time to move from this side going to this side because the diffusion surface is thick. But this side, it won't be as slow. It will be fast because the diffusion surface is thin. It is what? Thin. So thickness of diffusion surface, here the fact that how it affects is that the thinner the diffusion surface, the faster the diffusion rate. So meaning if the diffusion surface is thin, then particles will diffuse faster than when the diffusion surface is thick, because here the distance it's long. I hope we're clear, my students. Are we clear? Fidon Fika, welcome, Miss Helen. Are we clear on the thickness of diffusion surface? And please, if you don't understand nikufunza, this is the time, my students. This is the time to ask. Next year tufuna che ma1. So it's clear, Mr. Herod, it's clear, okay? Wonderful. So if you check this one is thick, this one is thin. So it will take uh, time for particles to move from this side to this side when they are penetrating through this thickness, because it will take some time. But here, because the diffusion surface is thin, the rate of diffusion will be fast, meaning particles will move going this side at a faster rate, meaning it will eventually turn to that. But you find that it will take time for these particles to reach this other end. Okay, therefore diffusion will be faster when they are penetrating through a thinner diffusion surface. Hope we're clear with that point. And then temperature. 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 I think on this one I can even go back to my shan. Okay. Temperature. Okay, now let's talk about temperature. So with temperature, increase in temperature increases the kinetic energy of particles, causing them to diffuse at a faster rate. So when the temperature is high, that will lead to an increase in the rate of diffusion. So like right now, the way it is hot, ngati muntu achaka perfume pa kama enda fast than when it is cold. Olo muntu ngati anunga chiwe che musaimvera fast mukakwera bus pacha, musaimvera fast because particles are moving at a faster rate, they're diffusing at a faster rate. So you'll find that yazaenda fast. Muntu angene chipepa cha mtu angene cheti pa mubasi, angene cheti pa mukamvera kudala. Olo muntu ngati anena perfume, as they are entering the bus, as long as they are wearing deodorant, as they are entering, you'll be able to pick it up because particles are moving at a faster rate. Why? Because it is hot. The way it is right now, it is hot because particles are gaining kinetic energy. Now, what is kinetic energy? This is what you learn in science, yeah, physics. Kinetic energy is the energy gained as a particle is in motion. So it's energy gained as something is moving. That is why you find that if a car is at high speed, it has got kinetic energy, whereby if it hits into something, ni damage hiyo. It will destroy that thing. Ngati angena mu fence, find that the damage will be high because that car has gained kinetic energy due to the increase in movement, the increase in speed. But ngatienda chepang'ono, it won't gain kinetic energy. So the impact won't be that much. Are you following? So kinetic energy is the energy gained as a particle is moving. So when there's an increase, remember, particles are in constant motion. Those who are doing chemistry, when you're looking at the arrangement of particles in gas, liquid, solid, you know that particles are in constant motion. Particles are always in constant motion. When it comes to particles that are in solids, they vibrate at one position. So all particles are in constant motion. When they are in when there's high temperature, those particles will gain kinetic energy because they're already in motion, and now they've gained the energy from temperature. They'll start vibrating, or they'll start moving fast, causing them to diffuse at a faster rate. So increase in temperature increases kinetic energy of particles, causing them to diffuse at a faster rate. That's what we need to know when it comes to temperature. Are we clear? Are we clear on temperature? Before we move on, Taonga Fileu Fuika Vasa. Thank you very. I hope I'm glad. I'm glad that you're understanding. So we can move on. Okay. Okay. Okay, sir, kindly explain again. Okay. So under temperature, I'll give practical examples. Yeah. Bus pajangati mukulaga bus. You will notice that muntu ankala kusogolo kwa motoka. Kusogolo, maybe you muli ku back seat. Imagine you're at the back seat. Muntu ali kusogolo kuja kuliwa driver. Uja muntu ngatavala ka perfume kaja kakale. Angena chembasa tipa kafika kudala where you're seated. Because particles will move at a faster rate right now the way it is hot. So if there is high temperature, particles they move faster because they tend to vibrate faster. Okay, when the temperature is high, particles move faster. Why? Because particles gain kinetic energy. Now, what is this kinetic energy? Kinetic energy is the energy gained as something is in motion. As something is in motion, it gains what? Kinetic energy. Pechivendera chintu, as long as chintu chivendera, it will gain what? Kinetic energy. So when you increase the temperature, it will lead to that particle gaining more kinetic energy because it's already in motion. Remember, particles are always in motion. Particles are in constant what? Motion. Even particles in a solid. For particles in a solid, they vibrate at one position. So when it's hot, particles will gain kinetic energy, which will cause them to vibrate fast, leading them to move at a faster rate. So what you just need to know is that when the temperature is high, particles move at a fast rate. Ndiye paja ngati muntu angena mbasi ka perfume kafika kudala. Olo ngati anunka chiwe, mwambila kudala mwini ku back seat. Why? Because particles are moving at a faster rate. Okay? So that's what we need to know when it comes to what's this? Temperature. So when it is cold, ndepaja tunsansa chi perfume anso ngati si perfume yako you've just asked we mpemba ko perfume, they give you their perfume, you spray careless suzimvera nozimvera sinamveke sinamveke it's just cold. When it's cold, particles they move slower than when it is hot. So right now if you just put tungono chefu tuzamveka. Yes. So that's how temperature affects the rate of diffusion. The higher the temperature, the faster the rate of diffusion. Okay, wonderful, wonderful. Now let's look at size of diffusion particles. Even self-explanatory. The bigger the diffusion particles, the slower the rate of the slower the diffusion rate. The smaller the diffusion particles, the faster the diffusion rate. So when the particles are large, diffusion will be what? It will be slow. But when the particles are small, diffusion will be what? It will be fast. Because obviously when something is large, even the movement, it will be slower than something that is small. Okay, so the larger the diffusion, the larger the diffusion particles, the slower the diffusion rate. The smaller the diffusion particles, the faster the diffusion rate. On this one, I don't know if I have to explain further because self-explanatory. So the larger the diffusion particles, the faster the slower the rate of diffusion. When the particles are large, when they are big, find that they'll move slower than when the particles are small. Simple, isn't it? Yeah. Now let's look at the importance of diffusion, which is the last thing, and then we can call it a day. So diffusion. Uh, so apart from temperature, there's a question here. Let me just highlight it from Mary. Apart from temperature, is there any other effects that can affect the rate of diffusion? Yes. So one is size of particles. We talked about concentration gradient. We talked about diffusion surface area. We talked about thickness of diffusion surface. Those are other factors that can affect the rate of diffusion, Mary. Okay. So importance of diffusion. Why is diffusion important? Okay. So diffusion is important in living organisms in the following ways. Number one, oxygen moves from the lungs to the blood and from the blood to the tissue cells by diffusion. You will learn this when we look at respiration. Okay. Carbon dioxide moves from the tissue cells to the blood and from the blood to the lungs by diffusion. So carbon dioxide that comes from the tissue cells, it will move from the tissue cells going into the blood, and from the blood going into the lungs, and then from the lungs it comes out because of diffusion. Okay. Dissolved food moves from the blood into the tissue cells by diffusion. So when you eat your food, that food goes into the stomach, or when you eat food, you put it into your mouth, you chew it, you swallow it, it goes into the stomach. Then in the stomach, there's a stage known as absorption, where the body takes up the food, the nutrients. Then those nutrients will now be taken into the blood. Then the blood will transport those nutrients, taking them to the tissue cells. And then the nutrients will now diffuse out of the blood, going into the tissue cells by the process of diffusion. So dissolved food moves from the blood into the tissue cells by diffusion. Okay. Hope you understand on the third point. Just to repeat, when you put food into your mouth, you chew it, it goes into your stomach. In your stomach, in your stomach, it goes into the small intestines, and then there's a stage, okay, which is known as absorption, where the body now takes up the nutrients from the food you were eating. So ngati muva okudya muja mwese ma proteins tupiza tenga ma proteins. Those proteins will now go into the blood. Then they will be transported by the blood, taken to the tissue cells. Remember the tissue cells? What do they form? Tissue cells, they form up an organ. Vectors opposite last week. So the tissue cells will receive the nutrients by the process of diffusion, because the nutrients will diffuse from the blood going into the tissue cells, so that those tissue cells will be able to sustain themselves, and they'll be able to ensure that the organ they are forming up is healthy. Okay. Metabolic wastes such as urea move from the tissue cells into the blood by diffusion. So urea mtundo. Iyi urea ipezeka mu mtundo. Okay. Iyi urea ichokera mu blood. Ikachokera mu blood yenda mu renal tube. You'll learn about this when we start looking at excretion. Otherwise, metabolic waste such as urea moves from the tissue cells into the blood, and then it will also move from the blood going into the renal tube, and then there'll be like secretion. All those things you're going to learn under excretion. I wouldn't want to go into much details. Maybe I might confuse you. Otherwise, urea, which is a metabolic waste, it moves into from the tissue cells into the blood by diffusion. By the way, when they say metabolic waste, what do they mean? They simply mean things that are produced from metabolic reactions which are not needed. Remember metabolic reactions? We talked about what? Catabolic, anabolic. Nikuuzani, do not forget the things that we are learning. Anabolic reactions, catabolic reactions, we were talking about those things last week. Those are metabolic reactions. So if we're talking about metabolic wastes, these are just things that are produced from metabolic reactions. Things that are not needed, things that are not needed, and they are produced from metabolic reactions. They're known as metabolic wastes. For example, ngati mpika kansima, yeah? Kaja kansima, kopo kwacho chikwangwa simuchifuna, it becomes a waste, isn't it? It has been produced in the process of producing the main thing, which is nshima. But you don't want the chikwangwa, you want the main thing, which is the nshima, isn't it? So what will happen to the chikwangwa? It becomes a waste, isn't it? Same with metabolic reactions. You find that during a metabolic reaction, something that is needed is produced, but in the process of producing that thing, there is another thing that has been produced which is not needed. And that thing is a waste product, which has to be removed. It is toxic, it has to be excreted. Okay. So an example is urea. So urea moves from the tissue cells into the blood by diffusion. Carbon dioxide needed by photosynthesis, needed for photosynthesis by plants, moves from the atmosphere into the leaves by diffusion. The carbon dioxide that you breathe out, it goes into the plants by diffusion. Oxygen produced during photosynthesis moves out of the leaves to the atmosphere by diffusion. My plants here such that produce oxygen. After photosynthesis, the oxygen is actually diffused from the leaves going into the atmosphere. Water vapor moves out of the air spaces of leaves to the atmosphere during transpiration by diffusion. We're going to learn more about transpiration once we look at transport in flowering plants. Otherwise, my excellent students, this is where we end, and it's exactly 21:01. This is where we end. If at all there are questions, you can ask. Otherwise, I hope you've understood what has been explained. Have we understood? Is everything clear? Is everything clear? Fiaumfuika? Namumfwa? Chivemba. Wonderful, 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 wonderful. So we'll continue tomorrow as we look at osmosis. So tomorrow is the day for osmosis. Today we've covered diffusion, and tomorrow I'll give feedback to assignment 2. So yeah, I hope we are studying. Please make sure that you study. This Friday we are having a workshop, and during this workshop I'll talk about how to make a study timetable, because we need one. You need one. You need a study timetable. So Pevika Livingono, please make sure that you study these things. Study the notes, watch the videos, attend the live classes. That's what it takes. Okay. I hope we've understood what was taught in tonight's live class, and I hope you've enjoyed. Make sure that you leave a like and subscribe to the YouTube channel. Otherwise, we can end here for today. We shall continue tomorrow, same time, 8 p.m. I'll be live Pamene Pano. From me, Philip Koma, excellent tour. Have a good night, my excellent biology students. Stay blessed.